Listen up, guys. Warning, caution, attention. Please follow all safety procedures within your company, your industry best practices, and the regulations within your area's jurisdiction. Let's repeat that. Follow all safety procedures within your company, your industry best practices, and the regulations within your area's jurisdiction. Let's keep ourselves safe out there, people. Take care now. Let's get into the lecture. Hey guys, this is Joe East here. This is part one of a series of lectures I'm going to do for battery ground fault troubleshooting. It's a very important issue in batteries, and it is a very expensive problem if you've ever had to do a ground fault location or troubleshooting. So let's get into the subject. Before that, for consultation, look in the bottom left corner of my slides here. You can contact me by email or text or phone. Leave a message on the phone or text. If I don't answer in the email, I'll get back to you as soon as practical. All right, let's get into this. So the easiest way for those who are not familiar with this concept to understand the concept is to use an analogy with something we're all familiar with if you've messed around with electricity in your life. So in this slide, I do some preliminary illustrations with regard to power, wall power, for say you plugging your computer into the wall or a toaster into the wall or some appliance into the wall. Normally it's called mains on some electrical standards, MAINS. Um, Mostly in the European context with IEC. Um, in the US, we just typically say wall power, 120 wall power in the USA or in North America. However, take a look at this diagram here. A single phase electrical power into the home and office. So you don't want, you know, high voltage like 380 or 480 to come into your home or your office unless you have something sectioned off safely to where you can access this high voltage. So in our home or offices, we're going to have lower voltages in the US, North America, 120 volts, and for most other places based on the European standards, it's going to be double that, which is approximately 240 or 230 depending on the country you're in. But that's irrelevant to the point. The point here is the setup of the three wires coming into your house. Okay, so you got three wires in your wall connected to your mains socket outlet. You have line, neutral, and ground. Colloquially, sometimes it's called hot. The hot wire, the neutral ground, and the earth wire. Those from the European extraction prefer the term earth. In North America, we prefer to say ground. For service engineers and service technicians, you can often hear the line conductor called the hot wire. In the USA, this is the coloring scheme for the wires. Check your local standards if you're not in the US or North America for the color codes specific to your country. So the line conductor is going to be with black insulation. The neutral conductor is going to have white insulation. And the ground conductor is going to be green or bare copper. Again, this is for North America, or those systems based on the North American standards. And below this illustration, I'll show you various cords. So there to the left, there's a NEMA 515 North America plug. In the middle, those of you out of the IEC countries, is Type C Euro plug. If you're in the UK, you have the plug to the right, Type G. And some of the Commonwealth countries have this type of plug. But what you need to notice In the diagram, it's a little red wire I connect between neutral and ground. So for traditional, customary, best practices purposes, the neutral in a building or a home is tied to ground at a single point, usually near the meter, usually at the meter. Some of the older schemes back several decades ago, maybe in the 50s and the 60s, the ground was connected to neutral at several different points, but the latest codes want it connected at a single point. And there are technical reasons for this, which we won't get into. So just note that for most electrical systems, the neutral is directly tied to ground at a single point as your electrical service entrance comes into your building or into your home. Just keep this diagram and circuit diagram in your mind, and we will discuss the differences between this and battery systems. It's very uh, similar concept, but with an opposite approach to battery systems. So this is for single phase electrical power for home and office, 120 volts for North American circuits. Okay, let's go on to the next slide. Now let's look at the difference between the service entrance to your home or office and a battery. So here I have the positive terminal, the negative terminal, and the ground. And notice the biggest difference is that ground is not connected to anything for this battery system. And this is the way it should be. By the way, if you're evaluating a battery system and if anyone connects a ground to the battery terminals of an energy storage system, my recommendation is don't do business with them, because that's an extremely dangerous system and you don't want to be anywhere near it. Okay, so here we have the three terminals, and ground's not connected to either one of the positive or the negative terminals. Now, complete isolation from ground in the ideal case, and we know that ideal is just useful for circuit analysis, but in the real world, the ideal won't exist, but it's a useful rule of thumb. So complete isolation from ground is the ideal, where the resistance is infinite between any of the battery terminals and ground. All right. Now for vehicle systems that don't have a ground, obviously there will be a chassis, or chassis ground in some cases it's called. So this isolation between ground and the battery terminals is commonly called floating with respect to ground. Um, don't confuse that with float charge, but a battery floating with respect to ground means that it's not connected in any way to ground. Let's go to the next slide. So let's look at the non-ideal case, which you will find in the real world. So what are the requirements that the positive and negative terminals of energy storage systems, whether in an electric vehicle or connected to a utility or a UPS, what are the requirements for isolation from ground of the terminals? Okay, so I just put a resistor in between the negative terminal and ground to illustrate. We have some resistance to ground. Like I said, the ideal is infinite, but in the real world, there's going to be some resistance to ground. The minimum requirement in the electric vehicles standards is 500 ohms per volt. And you want to use this if you don't have any standards within your industry. So if you're in the energy storage systems, depending on what industry you are, make sure the minimum requirement for your system is at least 500 ohms per volt. So for an example A, if you have a 120 volt battery system, let's say going into a substation, you want at least 60 kiloohms between ground and any of the terminals on the battery. And you want to be able to measure this and prove it. This is a safety mechanism of battery systems. For another example, let's say you have an energy storage system connected to the grid via inverters. Okay, it's typically going to be around 1,200 volts. Some of these systems are maximum. So you have a requirement of 600 kiloohms isolation between ground and any of the battery terminals. All right. So why do we need isolation? Well, if you have a battery over, say, 60 volts or over 50 volts, depending on the standard, you have a shock hazard. And if you're assembling batteries for electric vehicles or energy storage systems, these are over 100 volts, sometimes close to 1,000 volts. And you don't want your service engineers or your service technicians to be in danger of making a mistake and then being electrocuted. So it's a protection against a single point of failure of many, phenomenon with regard to electric shock. All right, so you want to allow the technicians and service engineers to be able to touch one point of the system with their hands without risk of electrocution. So isolation provides for this, what's called the one-hand touch. So a standard way of interacting with a battery system when you're repairing it and you're touching some of the terminals is to use one hand. That way, with two hands, an electric shock can go across your heart and give you a larger danger of cardiac arrest. However, if you're touching it with a single hand, well, then there's no circle it can make through your heart from your hand, and that way it's a safer setup if you design for a single hand touch that is a fail-safe. So obviously, if you put one of your hands on a terminal that's at the, say, 1,000 volts and the other one that's at 500, well, you still got a shock hazard across your heart that could do very bad things to you. However, if you're only touching any part of the system with one hand and your feet are touching the ground, well, then there's no danger if your system has isolation from ground. See where I'm going? But if you're single-handed touch the system and you have a ground fault, well, then there's a likelihood of getting electrocuted if your feet are grounded and your hand that you touch the system with is above a certain voltage threshold. Okay? So that's why we need isolation. It's another brace in safety, another prevention of single faults easily happening. And the main thing in battery work is the single hand touch, the one hand touch. Now, if you've ever worked on battery systems, there's, these are large systems, and sometimes you make mistakes. You might drop a tool. Let's say you're torquing a bolt with a wrench, and you can drop a tool inside the system. So there are mistakes that can be made with batteries, and you don't want it to be easy for somebody to hurt themselves with electric shock. Okay, so yes, we're dealing with high voltages, and if it's say a lithium battery system and you have low impedance, which high currents, low impedance, right? So you want to make the system safe for technicians and service engineers making mistakes, say dropping tools, you torquing down a bus bar, bolt, the wrench falls. You want to make it as safe as you can. And this isolation from ground is one way to do that. Also, you're going to need to repair the system eventually, maintenance and repair. So let's say after 5 years of service, you might need to go in and torque down some bolts that might have gotten loosened due to aging and thermal expansion and contraction over say certain temperatures over the seasons, right? So you're going to need to do repairs and maintenance. And also while you're assembling the system, uh, every module on an assembly line should be below 50 volts or 60 volts for touch safe purposes. But when you begin assembling modules into a system, you introduce the likelihood of electric shock. It's above 60 volts. So this isolation designed system is another way to protect the guys who are assembling the system after it's manufactured. All right. So there's a few reasons for isolation, and it's all related to reducing the chances of electric shock and allowing for a single hand touch of the bus bars that are connected to the battery terminals or the battery electrodes. That way, when it's got to be assembled, right? So you got to do some sort of connection from the module terminals to bus bars. So it has to be assembled in some way. So guys are going to be interacting with these bus bars and with the battery terminals. And we got to make sure that we reduce the chances of shock as low as possible. And isolation requirements and isolation design provides for this. Okay, we're going to cut the video off here, and we'll do revision in part 2 later on. Take care. Let me know if you have any questions, and feel free to contact me. And you guys, be safe out there. Thanks a lot. Take care.